Detergency is a field in which research is leading constantly to new developments. This film is a simple outline of how detergents work. The word detergent comes from the Latin detergere and means something which cleans, ranging from soap to the latest non-soapy detergents. Their chemical differences may be great, but all are designed to clean. The word detergent covers them all. Water by itself is not efficient at cleaning. Oddly enough, it isn't even very efficient at wetting. Look, the water doesn't give an overall surface cover. Instead, it forms itself into globules, shapes which have a low surface area for their volume. If we drop a globule of water onto a piece of fabric, it strives to keep its shape. It doesn't soak into the fabric. In fact, it doesn't wet it thoroughly. To understand why it isn't an ideal wetting agent, we'll have to know a little more about the nature of water itself, about the forces at work inside, say, a simple glass of water. If we could magnify water 100 million times, we would see a molecular world of unsuspected activity. For in water, forces of attraction exist between all adjacent molecules. Each individual molecule attracts its immediate neighbors equally, and at the same time is attracted by its neighbors equally. This applies to all molecules in the body of the water. But at the boundaries of water, this balance of opposing forces of attraction is disrupted. The pull of the molecules at the surface must change, because the forces of attraction felt and exerted by them can exist only sideways and downwards. This gives rise to a certain tension at the water surface. We call this surface tension. Here we are dealing with a water surface between water and air. But what happens is typical of a water surface between water and any other substance, solid or liquid. It occurs at the sides of the glass. The overall name for this phenomenon is interfacial tension, and surface tension is just one aspect of it, though its effects are the easiest to see. In nature, this is excellent for the pond skater. In fact, because of surface tension, all sorts of surprising objects can be supported. But add a detergent. The objects sink because the surface tension is reduced. With individual globules of water, the effect is the same. A detergent enables the water to soak into the fabric. Reduction of surface tension is the first of a detergent's functions, for once a fabric is thoroughly wet, the dirt becomes accessible. Let's have a look at a normal everyday fabric and see just what dirt is. Dirt is foreign matter, any substance which has got into the wrong place. It can be broken down into three main forms. First, there is grease or oil. Then there are particles of dirt, like dust. Finally, there's dirt like salt or sugar. This is easily soluble in water and is no problem. It's greasy dirt and particulate dirt which cause the most trouble. For our purposes, as their characters are rather different, it's simpler to treat them separately, but it should be remembered that in everyday experience, they are usually mixed up together. First, we'll take some particulate dirt, simple household dust. In water, most of it floats. None of it is really wet. And agitating it doesn't seem to help. Now some oil, stained red to show up better. Agitating the oil does succeed in breaking it up a little, but the drops of oil soon merge together again. The effect of agitation is only temporary. But now, add a detergent. The change is startling. With only a little agitation, the dirt particles are evenly suspended throughout the liquid. With oil, it's a similar story. This time, the globules break up and stay broken, dispersed in the liquid as very fine droplets. This is the second of a detergent's functions, the breaking down and suspension of dirt. To understand how it does this, let's see how a typical detergent molecule is constructed. This is a soap molecule, magnified several 100 million times. It's only one kind of detergent molecule among many, but it's fairly representative. The molecule is a paraffin chain salt, a long hydrocarbon chain with a water-soluble group of atoms attached to one end. This group has an affinity with water. The hydrocarbon chain has quite the opposite. More simply, the molecule has a head which loves water and a tail which dislikes it intensely. So in water, the molecules try to make for the surface, where their heads can remain in and their tails can be pushed out. In this way, they reduce the existing surface tension. This explains how a detergent affects the individual globule of water. The detergent molecules tend to collect at the surface, where they reduce surface tension. This weakens the form of the globule, allowing the combined water and detergent liquid to spread out more and so wet the fabric more completely. In water, the molecules don't only migrate to the surface, they also bunch in protective clusters, with the tails turning inwards as they try to avoid the water. These clusters are called micelles. In water, the tails will make for any non-watery surface they can find, reducing the tension between that surface and the water surrounding it. These surfaces obviously include the fibers of any fabric placed in the water. The detergent solution soaks right into the individual fibers, displacing the odd films and pockets of air, which water alone couldn't penetrate. The micelles act as reservoirs of detergent molecules, ready to come into action as required, to remove dirt. The detergent molecules are attracted by the particulate dirt, which gets both on and between the fibers. The water-hating tails settle on the particles, the water-loving heads facing outwards. When the fabric is agitated, these particles are easily worked free. They are suspended in the solution by the detergent molecules. It's much the same with greasy dirt. The tails of the detergent molecules like grease and oil. Where grease is embedded in the fabric, the tails will root into it and start to separate it from the fibers. The grease tends to roll up into minute globules, the detergent molecules surrounding them like pincushions. Shaking things up frees the grease from the cloth and breaks it down into still smaller globules. They are soon dispersed throughout the liquid, rather more thoroughly than in the case of particulate dirt. We can actually see dirt being removed. First, oil from a single fiber. Now, a piece of fabric. On it, smear some oil and some particulate dirt, held together for the purposes of this experiment with a little grease. Then place it in a detergent solution. The detergent gets rid of the bulk of the dirt very quickly, though before the fabric could be fully cleaned, naturally agitation would have to be much more thorough. During the process of washing, the detergent solution accumulates in suspension a considerable amount of dirt. It's important that none of this finds its way back to the fabric. Two other factors help here: agitation, obviously, and electrical repulsion. In a detergent solution, electrical repulsion occurs between the fibers of the fabric and the particles of grease and dirt, for they are all surrounded by detergent molecules, and a detergent, like a simple salt, is an electrolyte. In water, the detergent heads are negatively charged. Since like charges repel, the dirt stays evenly dispersed throughout the liquid. Agitation helps here as well. In fact, it is an essential part of the washing process at almost all its stages. The foamy lather has very little cleaning effect, but it does indicate that the detergent is still active. When the fabric is taken out, there is bound to be some dirt and detergent still clinging to it. When this has been rinsed away, the washing process is complete. To sum up, water itself is not an ideal wetting agent. A detergent weakens surface tension. This is the first of its functions. The second is the removal and suspension of particulate and greasy dirt. Remember that when a detergent is at work removing greasy and particulate dirt from fabric, electrical repulsion plays a part, and that agitation is essential. Soapy or non-soapy, solid, liquid or powder, this is how a detergent works.